Howdy everyone, welcome back for our Chapter 6 example problems, where quantum mechanics are going to confuse the heck out of us all, but that's okay. These problems can be a little tricky for a lot of students. There's a lot of places where people go wrong. Sometimes it's with the setup, sometimes it's with just getting it into the calculator. So we're going to do a few more examples in this one just to kind of make sure we have everything where we need it, and hopefully give everybody as many examples as they need to get these all correct. So let's go ahead and get started. And we're going to start with three problems about light. All these equations are going to be using the same equation or two, that either it's the energy of a photon of light is equal to h nu, the Planck's constant times the frequency, or that the energy is equal to h times the speed of light divided by the wavelength. These are the same thing, it's just subbing in for frequency the speed of light over wavelength, but we'll use whichever one's appropriate and rearrange as appropriate. But this is where we need to be for these three problems. So it says, what is the energy of a photon, so we're solving for E, with a frequency of the 2.94 times 10 to the 14th reciprocal seconds, or hertz. So that just means, hey, we're going to use this equation as is. We want energy, we have frequency, and we can plug in Planck's constant. It's a constant. So we just plug in energy is equal to 6.626 times 10 to the negative 34th joule seconds. That's Planck's constant. And then times the frequency. We're in seconds, so it's all good. 2.94 times 10 to the 14th reciprocal seconds. Notice that means this seconds will cross out with that reciprocal seconds. We'll be left with joules. That's energy, so that's good. So now we just need to plug it into our calculators with proper scientific notation. All right, times 2.94 times 10 to the 14th. And we get, let's see, 3 sig figs, so 1.95 times 10 to the negative 19th joules. And that seems reasonable for that frequency. This is going to be around visible light. It might not be exactly visible, but it'll be close to it. So that's our final answer there for part A. Okay. For part B then, now we're going to do energy of a photon with the wavelength given. So that means we want the E equals hc over lambda, so we can plug wavelength here in the denominator. Now the thing to remember is that c, the speed of light, is 3.00 times 10 to the 8th meters per second. That's meters, but here we have nanometers, so we've got to fix that. Otherwise the units won't cancel out and we'll get the wrong answer. If you need more sig figs, it's 2.998, but that's all in the back of your book if you need it. All right, so let's go ahead and start this out. For our energy equal to, again, Planck's constant, 6.626 times 10 to the negative 34th joule seconds. The speed of light, 3.00 times 10 to the 8th meters per second. And then now for our wavelength, we can't just plug in 413 nanometers, but we can do a little trick where we don't have to make it exactly meters with proper scientific notation. We just say, well, wait, what does nano mean? Nano means 10 to the negative 9th. There are 1 billion nanometers in a meter. So if we just apply that 10 to the minus 9th, then we can leave the 413. So we can say, oh, okay, it's 413 times 10 to the minus 9th meters. And so I encourage you to remember that nano, we don't use it very often outside of light, but here in chapter 6, if you can remember that nano means 10 to the negative 9th, you will save yourself a lot of time and effort. All right, well, now we've got everything set in. Meters will cancel, the seconds cancel, we're left with joules again. That's what we want. Now we just need to plug it in. So we have 6.626 times 10 to the negative 34th times 3.00 times 10 to the 8th divided by 413 times 10 to the negative 9th, and we get actually a pretty similar number to the other one, 4.0 8, 1 times 10 to the negative 19th joules again. So, yep. When you see 10 to the negative 19th, you're around visible light. It might be ultraviolet, it might be IR, but when I see 10 to the negative 19th, I know I'm close to visible light. And so that seems reasonable because 413, that's right at the edge of visible to ultraviolet. That's in the very deep purple. Okay. All right, now for part C, where it does get a little bit trickier. This time they want us to find the wavelength of the photon with the energy. So they will start again, E equals hc over lambda, but we want to solve for that. So we're going to cross multiply those two and say that, okay, lambda will be equal to hc over energy. And I can't encourage you enough to rearrange equations before you plug in the numbers. Think about all these scientific notation numbers we've got. If you try to plug them in over here and then rearrange, that's when things go wrong. So go ahead, rearrange it while it's just letters, make it nice and easy, and then plug in from there. So we will say, okay, our wavelength is equal to Planck's constant, joules seconds, times the speed of light again, and now it's divided by the energy, so 6.06 times 10 to the negative 19th joules. So again, I'm expecting something close to visible. Joules cancel, seconds cancel. We're left in meters, which is good. That's a wavelength. So now we plug it all in. If you have a graphing calculator, which you're not really supposed to for this one, but if you have a multi-line calculator, for this class we can punch in this whole thing all at once. I still encourage you to do it one step at a time, because with all the scientific notation, if you don't punch it in right, either using the EE button or the EXP button or using parentheses, something's going to go wrong and you'll get this really weird power of 10, and if you don't catch it that it's weird, well then you're just going to have the wrong answer. So for this one, it is 3.28 times 10 to the negative 7th meters, and that is correct. Now, if we wanted to put that in nanometers, because a problem might say that, hey, put this in nanometers, we would multiply by 10 to the 9th, or divide by 10 to the negative 9th, whichever way, and this would be 328 nanometers. Sorry, bad penmanship again. Either answer would be appropriate, just depending on what the actual book wants you to type in. But again, this is in the ultraviolet, so yeah, 10 to the negative 19th into the ultraviolet. Okay, makes sense to me. But yeah, that checks out. So there are 3 examples. A lot of times, B and C are the more common ones that the book will give you. Either solve for the energy from wavelength or solve for the wavelength from energy. Just make sure, again, that trick in part B, having to change the nanometers to meters with the 10 to the minus 9th, that's what you got to watch out for, most of all in all these problems. All right, let's move on. The next part of Chapter 6 dealt with quantum numbers and all the orbitals that the hydrogen atom can have and how they develop this idea of where are the electrons. They're not just in random places around the nucleus. But there are rules about what can these quantum numbers be, and so I wanted to do a quick problem with one of those to refresh those rules. So they give us that there's an orbital that has n equals 4 and L equals 2. So we're somewhere in the 4th row, and L equals 2, well that would be D. So we're somewhere in the 4D. But they want to know what are the possible values of m sub L. Well, first let's review the rule. M sub L is allowed to go from L all the way down to negative L by ones. Put 1 there so we know the difference there. So if L equals 2, that means we can go with 2 or 1 or 0 or negative 1 or negative 2. So that's our set of 5 that we could be, and that actually helps confirm that, oh yeah, L equals 2, that's supposed to be a d orbital. Well, yeah, there's 5 d orbitals, and look, there's 5 possible values. That checks out. If we have possible values of m sub s, then in that case, well, that one's easy. M sub s, no matter what, is always either the plus 1/2 or minus half. I'm just going to put it here for all electrons. Right? Those are the two possible values. Now, if you're in the same orbital, only one can be plus 1/2, the other's got to be minus 1/2. But if you just have a random electron in a hydrogen, that's the key for one electron, then it's plus 1/2, minus 1/2 for everything. All right, so hopefully that will help you kind of see when they do this, when they say, well, what are possible values to look for? Now I'm going to do a little extra one. Let's pretend that we didn't know that L equals 2. Let's say that we had something where it was n equals 4 and the m sub L equals 1. All right? And they want to say, what could L equal? What are the possible values there? Well, for that, L can be anything from n minus 1 all the way down to 0 by 1s again. And L, because of this rule here, that, well, L must be greater than or equal to m sub L. So we say, okay, m sub L is 1, so that means L has to be at least equal to 1, but it could also be 2, it could also be 3, but then it's got to stop there because L has to always be at least 1 less than n, so if n is 4, then 3 is the biggest one there. So this was kind of a little extra problem of which way, but considering some ways that the problems are presented, sometimes you're given n and m sub L, and you got to figure out L in between them. So that's how you do it. Say, well, it can always be at the same size. It can't be smaller. It can't be 0. But it could be up to 1 less than n. So there's our range for that. All right. Last problem. I'm going to do it a little bit differently from the book. In 6.75, it just wants the condensed form where you start with the noble gas shortcut and then move on from there. But just to make sure we have all the things done, I'm going to give all 3 types of configurations for nickel. I'm going to give you the full where we start at 1s. Then we'll do the condensed where we use the noble gas shortcut. And then we'll do the orbital box method where we draw the arrows. So if we do the full where we start at 1s, remember, we're going left to right across the periodic table until we get to the end of the row or the end of an orbital, and then we move on to the next one. So the first orbital is always 1s. We fill in both boxes in that first row, so it's 1s2. Then we move on to 2s, where lithium and beryllium live. We're filling in those boxes on our way to nickel, so it's 2s2 because we filled in 2 boxes. Then we move over to the right where it's the 2p because we're in the p block over there. We go from boron all the way through neon. We fill in all 6 with electrons, so 2p6. Next row is 3s where sodium and magnesium are. We fill in both again, so 3s2. Next comes 3p where we have aluminum all the way through argon. Again, we're filling in all 6 on our way to nickel. So 3p6. Next comes the 4th row, so it's 4s. Now here's where we don't have the gap anymore, so it's important to remember, s always stops at 2. It's only those first 2 columns. So we fill in potassium and calcium. That's the end of that, so it's 4s2. And now the trick where the d orbitals are always 1 less than their row. So we're in the 4th row now, but the d is 1 behind. It's 3d. And then we count how many boxes do we fill in to get to nickel. Nickel is the 8th box in that section, counting from scandium is number 1, titanium number 2, vanadium number 3, continuing on to nickel. So 3d8, and that's where we stop. If we check, we can count, say, 2, 4, 10, 12, 18, 20, 28, 28 electrons total. Nickel is atom 28. So that all checks out. Now if we want to do the condensed or the kernel method, depending on how you refer to it, that's where we start with the noble gas that came before, which would be kind of right in here. groups. That is going to be our argon core. That gets us all the way through 3p6. Then we say, well, hey, just what comes after argon? We're in the 4th row, so that's the 4s2, and then again the 3d8, and we can go from there. And then the final method is if we use the orbital method, the orbital box, where we use blanks. Now this one is very commonly combined with the condensed method. There's some problems on the homework where you got to click in everything, so there you'd be doing it from the full. But here we'll just combine it with orbital. We'll start with the argon core, and then we have 4s. There's 1s orbital per row, so we just draw one blank and label it 4s. Then we have 3d. As we saw with the m's of L's, there's 5 d orbitals per row, so we'll draw 5 blanks close together and label that the 3d. Now we put in our electrons. We have 2 electrons in the 4s, so they've got to go up and down. So up, down, that's to fulfill the Pauli principle. Then for 3d, we now have more than one blank. So the rule is 2 electrons per blank, 1 up, 1 down. But before we pair anything, we fill in all the blanks and spread them out first. That's Hund's rule. So 8 electrons, the first 5 go up, 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 up. And then the last 3 go down, down, down. So we would still have these 2 that are unpaired. That's how it's supposed to be. That would be the orbital configuration for nickel. All right, so I'm hoping that having this, same thing in all 3 forms, you can see how they're related. It is not a bad idea that even if the book's only asking for the condensed, or especially if it's asking for the orbital, not a bad idea to just write the full one out first, just so you then know what you're doing, until you get used to the condensed, where you can just start with the noble gas. But never a bad thing to do kind of all of them on your own first, and then just plug in the one that the book is asking for. All right. That's it for Chapter 6. Have a good day. See you back for Chapter 7.